going to be a great opportunity to look at the Polish side of the cultural background of Kopernik, both the facility and Mikołaj Kopernik himself. Test. Is it coming through now?
Could you do that again?
Testing. No, still nothing. Let's try this.
It's definitely working.
Try it again. Is it coming through now? Testing. Nope.
That's working.
I'm not hearing the usual static either.
Try it again. Is it coming through now?
It is?
Okay. And then we'll
I'm
leave
just
it.
not hearing it.
Yeah, I'm not sure why. It's not registering there, but thank you, Laura.
Alright, whatever you did fixed it.
Bring it down there. Okay, sorry about that. We're actually streaming this live right now, so that's why you may hear the mic working fine, but we didn't hear it properly on our end through the stream, so we were making sure that was working. So those online can enjoy. I'm holding to our camera's up in the ceiling there watching me. It will track me throughout the program, because I will have some demos to show throughout the evening too. Yeah, lots of programs coming up. We are organizing a holiday event at Kopernik as well. If you got to participate in Hocus Pocus for Halloween, Holiday Horizons is coming up, and it's a comparable event, very family friendly, and we're hoping to at least offer that on 2 weekends in December. So look forward to that as well. Tickets will be made available in a similar manner to Wigalia there. Okay, one thing I want to show you on our website too is at the bottom of the page there is a place called Clear Sky Chart. And on the Clear Sky Chart, this will show you an astronomical overview of our forecast at our site. So the most important thing there, of course, at the very top is cloud cover. Ultimately, what you want to see across the board here is dark blue. We don't have that tonight, unfortunately, but raise your hand if you got to go look at something through the telescopes. Okay, all right, good. That's good amount of you. I'm glad we got that covered now, just in case it gets worse, although from what I'm seeing on the Clear Sky Chart, it looks like it should stay pretty constant now. This kind of lighter blue teal color, you're talking like 50% cloud cover there or so. So not the greatest conditions, but we have a moon tonight, which is good for this kind of weather. It'll pierce through those clouds, and we can certainly go out and observe that again. We have our 6-inch telescope out there, our Spring-Sonian, so there's some variety to observe tonight. If the conditions are even more optimal, then the planets will come through as well, like Saturn and Jupiter. So we'll see what happens on that front. There's also transparency and seeing here. Those are two other characteristics of the sky that are important for astronomy. You want strong transparency and seeing. We've got the greatest detail on both planetary objects and deep sky objects. So that's what we're looking for with those two. The better the seeing and transparency, the more detail you get. Tonight it's not great. Transparency is okay, but seeing is not optimal. So there, on a night like somehow, yeah, Saturday's looking a little better, where you have this darker blue. Seems to be a recurring trend for this fall. Saturdays are always great. Our Friday nights where we're open, not as nice. But anyways, Better seeing would give you more optimal views of planets. So if you see a Friday night that's dark blue across the board, it will be a huge distinction from what we're seeing this evening in regards to planets and deep sky. Okay. So that's enough with the website. Last thing I'll show you here is we are on YouTube. As I mentioned earlier, this program is being streamed right now. So you can visit the Kopernik Observatory YouTube channel. You can subscribe there and stay up to date on the latest major astronomical events. And all of our Friday night programs are put out here unless there's some kind of copyright issue. So those are available to you as well. The video we've had posted at the front of our homepage for a while now is the making of the Kopernik Science Park, which you may have seen in the darkness out there, or maybe you've been to the science park as well. That's always a fun video to go back to, a little behind the scenes on our science park. And finally, actually, the last thing I'll mention back on our homepage. One of the things that we offer here at Kopernik are memberships. And if you go to support and become a member, you can actually become a member online. It's really easy, or you could submit a paper registration form. What's great about this is that not only do you get into Kopernik programs for free every Friday night, you also become a member of the Association of Science and Technology Centers, or the ASTC. And that gets you into science centers, museums, that are associated with ASTC around the country for free, in most cases. I would say in the majority of them, it is going to be free admission, but you can always go to this link here to see exactly what they offer. If you're planning a trip sometime soon, it's usually way more cost effective to become a member at a science center than to just pay the admission. Just an admission for 4 people is often more expensive. So it's a little trick, and it's also a way to support Kopernik. Just as an example, a museum you can attend is the Intrepid Museum in New York City, where you can actually go see a space shuttle, and see it at full scale, not this one. This one's cool, of course, it's our space shuttle, but it's 1/16 scale. Imagine how big the real one is. So you can actually go to New York City and attend that museum for free if you're a Kopernik member. And I recommend doing that because the space shuttles in person are just truly incredible. With that said, though, lots to learn at Kopernik.org, but today we're here to learn about black holes. And we're going to jump into that now. And this is black holes on Black Friday, very topical. And hopefully you had a nice holiday here, and I hope your day today wasn't too busy. But we can wind down a bit with this discussion on black holes. And I promise not to get too existential with them. All right, let's move to our first slide. Talking about the life cycle of a star. I think this is a great place to start because this is the origin of black holes. They're a part of the stellar life cycle, and they're not guaranteed. It all depends on your solar mass. So just looking through this diagram here, in the start of the stellar life cycle, you have a nebula. A nebula is going to be filled with clouds of dust and gas, primarily hydrogen. Depending on how old the nebula is, there may be some heavier elements in there as well, but primarily it's going to be a hydrogen cloud. And within this cloud of hydrogen, you have dust clouds, and you have these globules form in those clouds. The gas starts to combine in certain areas. It pulls in because gravity starts to get stronger and stronger, and you start to get denser and denser material in that zone of the nebula. And once it gets dense enough, the temperature really starts ramping up, and you get a protostar. This is just a quick overview. We're going to go through some more detail of each of these phases of the stellar life cycle. Now, Sometimes, if the protostar doesn't have enough mass to truly kick off that process of fusion, you'll just end up with a brown dwarf, which is kind of like a hot Jupiter. They're usually a little more massive than gas giants like Jupiter. They're also going to be made up of hydrogen, primarily, maybe some helium. But you can see, if you can see enough detail on it, it has kind of those signature stripes that gas giants sometimes have. They're more or less hot Jupiters. Then you jump into your main sequence stars. If you have more mass, you'll become a star like ours. The sun is along the main sequence line. It's a pretty average star out there in the universe. And after several billions of years, that star will eventually start running out of fuel and become a red giant. And then following that, we get a white dwarf and a black dwarf, which we'll go into. And if you have a main sequence star, or even branching outside the main sequence, something that's really massive, that's where you follow this through line. When you have a red supergiant, you get a supernova eventually, one of the largest cosmic explosions in the universe. And following that, you end up with a neutron star or a black hole. So we'll return to this life cycle of a star throughout the program, but that's a quick overview of what we're talking about here. So, getting into star formation, this is an example of a nebula. It has a couple of different names. Usually when it's a wider field, we call it the Eagle Nebula, and we can kind of point out the eye socket of the eagle, right, and the beak stretching out. But when you're zoomed in like this, it has a second name, known as the Pillars of Creation. And it's a pretty apt description, because this is where stars form. And as you may have heard, coined by Carl Sagan, we're all stardust. So we all of the matter in the universe originated from stellar, well, I should say all the complex matter, like what we're made out of, organic molecules, comes from stars that have reached the end of their cycle, and they fused enough elements to eventually produce those higher elements that we have that build up life as we know it and the universe as we know it. So, Pillars of Creation in visible light on the left side, taken by the Hubble Space Telescope, and Pillars of Creation on the right side, taken by the James Webb Space Telescope. So this is a very recent image. And one neat way to tell the difference between what's a Hubble telescope, or most space telescopes, versus a James Webb image, if you look over here, you see on the brighter stars, there are these diffraction spikes. And those have to do with the shape of the mirror and the truss structure that supports the secondary mirror. So on Hubble, it's a circular mirror. And you get these 4 diffraction spikes in total. The James Webb Space Telescope mirror is different. In fact, if you look, those that are here, if you look in the back of the room, you can see that gold mirror on the wall with JWST underneath. That is I think it's just over a 12th scale model of the James Webb mirror. So the real one's 12 times bigger. And you can see it's made out of hexagons. And it takes on an overall hexagonal shape. And because of that, we get our 6 diffraction spikes in our brighter stars. So that's one way you can tell the difference between the two. See 6 diffraction spikes, that's a pretty unique mirror design, so you know it's James Webb. The opposite isn't true. If you see 4 diffraction spikes, it could be almost any telescope. Most of them have a circular mirror. So this is where stars are forming in a nebula like this. It's not the only one, of course. Stars are forming in every galaxy out there in the universe, and we have many nebulae in ours. Coming up here in the winter, one of the nicer ones is going to be the Orion Nebula. You can even see the Orion Nebula with your eye at Kopernik. But of course, it pops even more through a telescope or through binoculars. And when you look at a nebula, you're seeing a stellar factory. And these redder stars around the pillars, those are newer stars down here too. They are successful stars. They are undergoing the process of fusion. And then if you look closer in, this is where the Hubble telescope view really helps, because we can see these globules that we talked about before jetting off. All of those areas that are kind of popping off the pillars there are where stars are forming. So that's where you're going to kind of enter that protostar phase. But these stars are successful, and they have started spreading out beyond the nebula. They've taken in they've kind of taken in the fuel around it as well. So at one point during their formation, the nebula may have stretched out further this way, where these stars are, and up there, but they've utilized that fuel to promote that process of fusion. One last note on the James Webb image. If you're familiar with James Webb, you know it's one of the best telescopes ever designed. It's a space telescope out there at a Lagrange point, so it's a good distance away from Earth, and usually wherever it looks, it will pick up a galaxy. So if you look at a variety of James Webb images, even if it's focused on a nebula, oftentimes you'll kind of see a galaxy in the background somewhere. Not in this case, though. If you look around the sides of it, you do not see any galaxies there. And that's because Eagle Nebula is right in the disk of the Milky Way. And whenever we're looking into the disk of our galaxy, which we can see during the summer really well here, you're looking through the interstellar medium for our galaxy, and you will not see any intergalactic galaxies, I should say. We need to look off to the sides of the band of the Milky Way across the sky to see those. So kind of a neat feature there. Depending on where James Webb looks, either we'll see some galaxies or none at all. This kind of like lava texture you're seeing at the top of these pillars, that's another feature of stellar formation. That's actually that ionization process of hydrogen. It's glowing in those zones because, again, those are where the stars are forming. So there's a lot of energy going on there, so much that it's ionizing the hydrogen in that spot, and it's glowing. Most of the time, hydrogen is going to appear as a reddish color in James Webb images, and even visible light as well. Like when we take a visible light image, usually when we find glowing hydrogen, it's going to take on a reddish or pinkish color. This is an infrared image, so they have to color match a bit. And we have a great presentation on this topic. They can go back on our channel that goes in depth about how they color match this to make practical and scientific sense. But it is a lot of color theory to make sure we understand what's going on in this for an object that we actually can't see with our eyes, or at least not in this way. We see it if we could see it, ideally it would look more like this with visible light on the left side. But our eyes still aren't good enough. They're better with a camera to pick up this detail. Okay. So here's a nice animation of this process that plays out in nebulae. So you have the stellar formation in action. This is simulated from data collected by Hubble and by other observatories. I believe it was put together by the University of California at Berkeley. So they pulled that data together and simulated what's going on inside here in 3D space. And you can see as this gas, this is happening over hundreds of thousands of years, by the way. So these nebulae stretch out for light years and light years. They're huge structures. It's important to take that into account. Our solar system is already pretty incomprehensibly big. These nebulae are huge. And that's why it takes so long for this gas to clump up. And once it gets dense enough, you see it's almost a chain reaction the way it plays out in all these kind of tendrils. you get these ignition processes of the stars undergoing fusion and lighting up to become a protostar. So there's a whole bunch of stars out there in the universe. About 90% of them are called main sequence stars. The sun is one of those, but you can venture outside the bounds of a main sequence star too. So there's a variety of sizes and colors, from blue to red. So the color of the star does help you determine temperature. If you think about a flame, blue is going to be your the hottest flame, right? Blue to white in that range. That's going to be very high temperature. Your red flame is going to be very low temperature comparatively. That's the same with stars. They follow that same mechanism. It's plasma. So the way a visible light shines is effectively the same process. And that's what gives us this surface temperature here. So for context, our sun burns at around 10,000 degrees Fahrenheit at the surface. And the more the mass of the star, the brighter and hotter it will burn. So big stars burn bright and they burn quick. So more mass equals shorter life. And that's, in a way, as far as the development of our universe has gone, that's pretty important. Because the higher mass stars are where we get all of our higher elements from. So without those stars igniting pretty quickly early on in the universe and then dying pretty quickly, we wouldn't have developed as fast as time has gone on over the billions of years of our universe's life. So that's a pretty critical point, that the more massive stars have shorter lives. Now moving on to protostars. This is another James Webb image, and it's kind of from at least when I first started researching this one, came from a little unknown place. It's a dark cloud called L1527. And that's not one I recognized. It's in Taurus the Bull. And dark clouds are nebulous regions in space. So this is where we can find protostars. And there's a lot going on in this image. We actually do have these available. If anyone wants one after the program, I would be happy to give like one per family. They do come from NASA. It's a really nice print of this object, and it has a whole description of it on the back. So let me know afterwards if you'd like to grab one of those. So this protostar, there's a lot going on. First, you kind of see how this pulling of material happens. These two cones above and below the central protostar, these aren't being jetted out. There are structures in the universe that are like that will jet out material. We'll talk about an example of one later, more related to black holes. These aren't jets. These are funnels moving into the star. The star is pulling these in because this is the central source of gravity. So this is fuel coming down into the star. And not just fuel. Heavier elements are starting to build up a disk. See that kind of bar across the protostar? That's an accretion disk, and it's the early stages of a solar system. So James Webb was able to see a solar system forming effectively. This is what our sun looked like billions of years ago, before the Earth, before the main planets. There was the protostar at the center, and an accretion disk forming around it where the planets would pull material from. So, very early stages of a star's life. Now this is another example of one of those images. We're looking beyond the main disk of the Milky Way. So if you look behind, in the background of this protostar, a lot of these lights here, see how they're fuzzy? Those aren't stars. Well, there are lots of stars all in one place. All of these little fuzzy objects are galaxies. That's not even the target for this image. They're not looking for those. But James Webb can't help but find them. And I always love that feature of this telescope, is that they'll focus on a nebula, and they could remove those galaxies if they wanted to, but why would you do that? This is just a tremendous image to observe from an object in our galaxy versus objects beyond our galaxy. So, protostars are these contractions of gas and dust. They're pulsing, and they're ramping up to around 15 million degrees. So they're starting cooler, warming up to that 15 million, and if they can reach that point, that's where they're going to become a full star. They're going to undergo a process of fusion, and like I said earlier, if they can't reach that temperature threshold, they'll most likely just become the brown dwarfs that we saw earlier. Electrons are stripped off of their parent atoms, creating plasma. So that's what our star is made up of, is it's a hydrogen-helium plasma, releasing a great deal of energy through nuclear fusion. And you're also entering this phase where outward pressure in the gas balances the inward pull of gravity. I'll have a graphic to explain that a little further as well. But looking at when is a star, so we're moving on from the protostar, how do we identify when it actually becomes a full-fledged star? A self-sustaining fusion reactor. So, a forming star is considered a true star when nuclear fusion takes place at its core, and this is the process generalized. You're taking 4 hydrogen atoms, and the process of fusion is combining those hydrogen atoms to create helium and energy. And that's important because if you're looking at the masses of this chemical reaction, of this fusion reaction, there's more mass on this side, less mass on this side. And maybe we know an equation that where we get this energy mass conversion. I'm sure we've heard of it before. Equals mc squared. So this commonly, they know Einstein developed this equation in his theory of general relativity to explain energy mass conversion. So it shows you that we can get energy just out of mass. Mass can be converted. But it needs to go through this highly energetic process of fusion, which, as of right now, is only sustainable through stars, although it is something that's being worked on Earth, because if we can figure out how to sustain it here on our planet successfully, then it pretty much solves a lot of our energy problems. But it's also one of those things you hear, it's only a few years out, and again and again and again. So, no guarantees there. Okay, so here's a graphic depicting this process. You have a couple of isotopes of hydrogen, which is been mentioned in the previous slide of proton-proton chain. And this is what's playing out there. The hydrogen atoms will pick up neutrons. So these blue circles are neutrons. So if you have a proton plus 2 neutrons, that's tritium. If you have a proton and 1 neutron, that's deuterium. Regular hydrogen has no neutron at all, so these are isotopes. And when those combine through this process of fusion, and it's the dense core of the sun or a star, you get helium out and a neutron out, and you get your energy. And here's where that equilibrium balance comes into play. This is called hydrostatic equilibrium. As the protostars kick off that process of fusion, you have a balancing act that starts to happen where you have this outward gas pressure being balanced by the star's own gravity. And this is what keeps the star at the same effective size, because this process of fusion, it's expansive, it's explosive. So there's that outward gas pressure. But what contains it is the sun's gravity. And that's why we have these stable fusion reactors in our universe. Now, once this decays, that's where we start reaching the end of a star's life cycle, which we'll get to. So, I covered you out of time, not too bad. this is an HR diagram. HR stands for Hertzsprung-Russell. And this was developed to categorize the stars in our universe. And I'm sure if I mentioned main sequence stars before, I'm sure if you had to guess what are main sequence, you can kind of see a pretty immediate trend throughout the entire plot, and that's right from this end up into the upper left-hand corner. Those are your main sequence stars. Those are the 90% of stars in the universe. And the plot itself is luminosity versus temperature. And our sun is going to be right about here in the main sequence. So we're a really average star, which is kind of good for the prospect of maybe finding life out there in the universe one day and trying to find evidence for that, because there are a lot of stars like us. And they burn at around 6,000 Kelvin, classified as a G-class yellow dwarf star. Incidentally, that's not the true color of our star, though. When you look up in the sky, and I urge you not to look directly at the sun, but you know it does take on a yellowish color. When we draw just a general graphic of the sun, it's usually yellow. On this graphic alone, it's also yellow. But if you were out in space, you'd realize all of that yellowish color is coming from our atmosphere. It's coming from how it passes through, and ultimately the sun is more of a whitish color. It's a pretty good example of a pure, not quite a pure white light source, because there are gaps. It's burning hydrogen, so the spectrum does have holes in it, but it's pretty white in color. I have another graphic of the HR diagram that categorizes things. In these clumps that we saw, we have white dwarfs. In that cluster we saw towards the bottom, we have our main sequence. It depicts exactly where the sun is at around that 6,000 Kelvin mark. These are surface temperatures, by the way. So 6,000 Kelvin, you convert that to 10,000 degrees Fahrenheit for the surface temperature of the star. And up top, you start entering the realm of your supergiants. That would be where you find stars like Betelgeuse and Rigel. And as you may know, Betelgeuse is an example of one of the stars that astronomers watch very closely. And I would say media often likes to take advantage of the idea that the star's going to go off any day, which maybe it could, but the thing is you see those articles again and again. It gets repetitive. But it's possible. We might see Betelgeuse go supernova, and if it did, it would be extraordinary. The best stellar explosion that is safe enough distance away that it won't harm us, but visible in the daytime, potentially. So it'd be cool if that happened. So I understand why there's not an excitement. Focusing in on an individual star like our sun, this is, and even still for stars that are smaller or larger, they do take on this general makeup from their core to the atmosphere. So layers of the sun. We have a great graphic of this. If anyone is new to Kopernik and hasn't been on a tour today, we'd be happy to take you on a tour of the building, just to take a quick look around at our facility and what we have available. We have a wonderful depiction, physical depiction of the layers of the sun in the physics lab next door. But the core burns at 15 million degrees Kelvin. And this is where fusion actually occurs. This is where those photons that eventually reach Earth come from. What's fascinating about that is that it takes anywhere from 10,000 to up to 100,000 years for a photon being formed at the center of the sun. So the energy that we get from the sun can take up to 100,000 years to go from here to here, the photosphere, where it's emitted. So you may have heard that sunlight is about 8 minutes old or so. If you wanted to get really specific, it's 8 minutes plus, maybe give or take 10 to 100,000 years. So it takes time for that photon to exit the sun, because this thing is hyper dense. So a little fascinating fact about it. Going beyond the core, there's a radiative zone that reaches temperatures of 7 million Kelvin, convection zone beyond that, and then onto the photosphere, and this is the visible surface of the sun. When we look at it through a solar telescope with a filter, we're seeing sunspots like these. The sun is very active right now because we're reaching the peak of the solar cycle. That cycle plays out once every 11 years, and so we're seeing a ton of activity. The reason for that is because the sun's magnetic field is very chaotic, and over that 11-year time scale, those magnetic fields start to get all contorted and mixed, and that can't happen. As far as physics is concerned, that needs to be fixed, and eventually the magnetic field of the sun flips and stabilizes. And these areas, the sunspots, are these magnetic storms, where you're witnessing the field lines perturb the photosphere. And they're one of the main features that you can see through a regular piece of solar viewing equipment, or even just solar projection. The chromosphere is where you get your flares and prominences, like these ones here. To see those, you need something like an H-alpha filter, which we do have here. When we observe the sun, we use it from time to time. And then finally, the corona. This gets really hot. You can see it's much hotter than the chromo and photosphere, 500,000 Kelvin to 1 million Kelvin. So that's the atmosphere of the sun. And that's what you see during a total eclipse. More on that in a little bit. So here is a little comparison of at least two stars and one planet. We have Earth, we have the sun, and we have a red giant. Can you see Earth there? Yeah. Oh. So you can fit, across the diameter of the sun, you can fit 100 Earths. So it's just a tiny little dot compared to our star. And then we look beyond to a red giant like Betelgeuse, and we're not even seeing the entire thing, right? So you're kind of just hovering along a horizon of a red giant there. So when we talk about these massive objects, these stars varying in size, or even planets and moons, we look at them as they deform gravity. And this came from Albert Einstein's theory of relativity. And the way our modern understanding of physics explains this is that we basically have this fabric of space-time. And when you have a very massive object, or even any object that has gravity, you're actually warping space-time on a very negligible scale. But that mass actually distorts the fabric of space-time. And that's what this model up here does. So we're going to at least do a quick demo on this, and we'll come back to it once or twice more throughout the program. But just as a very brief demo, I have a very heavy mass that we'll use as our center of mass for our spandex universe. Sometimes this is called a black hole simulator as well. And really basic to build too. You could do something like this at home, even on a smaller scale. And you just need some spandex and a circular structure. And you put your center of mass right in the middle. And you can see it warps. And if anyone wants to stand up just to see that warping of space-time, you can. You should be able to see it from your vantage point. It is. It's a great model for it. And the heavier the object, the more it's going to warp. Cause a greater curvature in space-time. Yeah. We will eventually. We'll save that. Don't worry, we're coming to it. We'll have this available at the end of the program, too, for anyone to test out. So the fabric bends around objects due to the object's gravity. And one thing that Einstein's general theory of relativity predicted, and he came up with a theory in 1905, and it changed our understanding of physics completely. And it still drives our modern understanding today. So in 1911, he wrote a paper that predicted that our sun, our star, would deflect light coming from a distant star behind it, so that you should be able to see it around the edge of the sun. So this shows you, here's the Earth, right? Here's our sun, and here's a star behind it that should be obscured by the disk of the sun. But what happens is, as this starlight approaches the sun, and you can see it, if it was to follow, just going back to general physics, it should, disregarding gravity, keep going this direction, and we shouldn't be able to see it. But instead what happens is, because of that space-time curvature and our massive star, this gives us the apparent star location, so that we can actually see starlight behind the sun. Now, the trick of this is that you can't do it all the time because the sun's too bright. You really are hard-pressed to see stars around the disk of the sun, except for during these events. During total eclipses, the sun is obscured by our moon. And you see that glowing atmosphere of the sun around it. That's what you want to see during a total eclipse. It's the corona. And because it darkens the sun enough, leaving just the corona behind, you can see stars around. If there's planets out during the total eclipse in April, then you would see them in the sky because it darkens the sky enough. But only really during totality is that readily apparent. So there will be a total eclipse on April 8th. And so the best views of that total eclipse will be seeing stars that are technically behind our sun because of the curvature of space-time. So you're seeing some of these deflected stars here. And this Eddington experiment from 1919 proved Einstein's theory of general relativity, at least this facet of it, and the curvature of space-time based on massive objects. So they actually observed this from two different locations on Earth and measured the stellar reflection. So that parallax was kind of important there to understand this deflection. So for those interested, that was Frank Watson Dyson and Arthur Stanley Eddington who devised this experiment to prove Einstein's theory true. This is a good opportunity to just briefly talk about the eclipse coming up in April. It happens April 8th of next year in the spring. And it's going to be a tremendous event. It will be 97% covered by the moon here. But to truly see it in totality, best places to go are going to be Buffalo and Rochester. You got to go a little further north to get a good amount of totality. If you don't want to make quite that long of a trip, Syracuse would also work. You just won't have as long of a span. I think it's the difference of like a couple minutes to a few minutes. So the longer you can get, the better. Of course, it all depends on weather too. So we'll keep our fingers crossed. This last eclipse wasn't that great here in October. But our solar eclipse ambassador, Sasha, who's back here running the stream, she was actually down in Texas and exact opposite forecast from here and got to send us the live view of the sun from Texas there. So that was awesome. You can go back on our channel and watch that. But a very neat event coming up, and we're going to be having more and more programming surrounding that eclipse, so look out for that. So we've talked a lot about the stellar life cycle and mostly focused on the context of what a sun-like star does. So we've gotten to this main sequence star period, and now we can start thinking about stellar death. Like where do we go from here once a star like ours dies? It becomes something like this, a planetary nebula. Now, planetary nebulas, that descriptor, it's a carryover from early astronomy when early astronomers were observing these objects in the sky with telescopes that were not nearly as advanced as ours. They looked like planets. They take on this orb-like shape in the sky. They knew they weren't planets based on the way they weren't really moving. They moved along with the stellar background, where planet exactly defines as wandering star. So these objects didn't wander. They knew they weren't planets, but they looked kind of like planets. And so they take on this kind of circular shape. And that's just a carryover. Other than that, it's just kind of a confusing point when people are first learning about nebula. So keep that in mind. It's just the early descriptor for them, and it never changed. Here's some other planetary nebula. This down here is the Ring Nebula. And you see there's a common trend. Some of them do take on those jets or funnel-like shape, but they do often have this circular look to them. And in 3D space, it's important to keep in mind these aren't flat objects. These are three-dimensional objects. And because this is the next phase, once the star starts expanding, that hydrostatic equilibrium starts failing. It's blowing off its outer layers. And when you think of an explosion, it happens radially, right? So these, like this one is a great example, this one up here too. They're spherical, approximately, in 3D space. And if you think about it, that should make some sense. The reason you get kind of a ring shape from it is because when you look into a sphere, at the edges of the sphere, there's going to be more material there that you're looking through. Whereas at the center of the sphere, looking at it as a circle, right, in the sky, you're not looking through nearly as much. So that's why you get this ring shape. And at the very center of most of all of these, you have that white dwarf, the remnant core from that stellar expansive process. So, planetary nebula and white dwarfs, the layers we're seeing around it, that circular structure, are the outer layers of the sun. Effectively, what was once the atmosphere, the radiosphere, some of the interior, everything beyond the core, that's what got blown off in that expansive process. So the core is all that remains as the white dwarf, and it's very hot. It was, especially at first, it's the same temperature as we saw earlier, you know, those from like 15 to 20 million Kelvin, and over time it's going to cool down. So that's what eventually gives you that black dwarf star. These stars are mostly made up of carbon and oxygen. Those are the remaining. For main sequence stars, that's what kind of the end product for them. The more massive stars produce the heavier elements. And that concludes that phase of the stellar life cycle for a lot of main sequence stars. You get your white dwarf that cools down over time. The process of fusion is no longer sustained, and eventually you have no more light coming from it. At least no more visible light. Black dwarfs can be emitting infrared light, but they're not going to be emitting visible light. Oh, and just give you a context for how big it is too. They're about the size of Earth. That's roughly the same diameter on average, around 8,000 miles across, because it's the core of the star. Now, beyond this point, if we have a more massive star, like a super red giant, like we talked earlier, they have a couple options. They'll go supernova, regardless, around 2 to 3 solar masses. That's when stars are really going to go supernova. And I think on average, it's around 10 solar masses is where you'll diverge to get a black hole, versus below that, you'll get a neutron star in most cases. So it's all driven by mass. Black holes themselves are these intense gravitational fields left behind when those supermassive stars collapse and their cores collapse. And the reason that they're so big is that same process that plays out early on. Of course, they're large, but they do undergo an expansive process like our star will. However, it's on a much grander scale, and it's that failing hydrostatic equilibrium that we saw earlier. They're much larger than our sun. Like I said, 2 to 3 solar masses is where this really kicks off for neutron star, and then higher for black holes. And we saw the star's life cycle, and this is that splitting that happens. Gravity becomes so big that it compresses, forming our black hole. And I have an illustration of one here. If you're right up close to one, don't recommend, but if you are, you have your super high dense core. And what it really is, even this structure here, really isn't much of a solid body. It's really a shadow. Because black holes are black because they're the absence of light. Light is being absorbed. Light can't escape the event horizon of a black hole. So what we physically see, and we can say we have physically seen a black hole now, which I'll show you some pictures later, is the shadow. And as you get closer to the center, you reach a mathematical point called a singularity, which is this infinitely dense point of mass and gravity. Around it, you see this accretion disk of material. Some of it is in orbit on the outside. Some of it is rapidly being spun in to the black hole itself to cross the event horizon. So around black holes, there's a lot of light, but at the start of the event horizon, that's where you get that shadow. And this is what's happening at the center. At that infinitely dense point, the singularity, you have this infinite warping of space-time. And this helps explain why things can't escape a black hole once you cross that event horizon. Now, an important point to make with these is that they're not cosmic space vacuums. If they were, if black holes sucked in everything and anything in the universe, we wouldn't be here. They'd be a problem because they've been around, as far as we know, they play a large role in galactic formation. There's a supermassive black hole at the center of every spiral-like galaxy. And spiral galaxies have been around very early. James Webb is proving that a lot of galaxies took on that spiral shape. So, in that, again, going back to the idea of very massive, large stars, they burn bright, they burn quick. They're responsible for black holes forming. And black holes can coalesce. So if a black hole meets a black hole, you'll get a bigger black hole. And that's where we get our supermassive ones from. At the center, there is one at the center of our Milky Way. And we're okay, right? That's good. They're not sucking everything and anything in the universe. It's just really they're just sources of gravity. We just don't want to cross over into that event horizon. So here's an example of some mass exchange happening when a star reaches a black hole. It's not a perfect demonstration of scale, but black holes they can be smaller, but they are singularities, and they all have that event horizon. So if material gets trapped, a black hole is going to be much smaller than a star nearing it. But that infinite source of gravity is going to pull that material in. And you can see these jets coming out of it too. These actually are jets. They're not coming from inside the black hole, but they are a result of all of this energy and matter coming in from a star. You usually will only see those jets when the black hole is actively devouring a lot of mass. So orbiting a black hole, things can, this is another depiction of what we saw, but things can successfully orbit black holes. And again, as long as you don't get too close, as long as you don't reach that event horizon, and you're moving quickly enough, it's just orbital mechanics. It's just like the space station. That's a good example that, in fact, because the space station slows down due to our atmosphere, it's a low Earth satellite, they do have to lift it up and speed it up to keep its velocity and keep that constant orbit around our planet. That would be the same thing for a spacecraft orbiting a black hole. You just have to keep up your speed, keep up your trajectory, and you can successfully orbit a black hole. As soon as you slow down, though, that's when you start falling in and could potentially cross that event horizon. So when a black hole devours a star, it emits radiation that can be detected by X-ray telescopes. So those jets you usually see are seen in the X-ray wavelength, and that's what they're looking for when they're looking for sources of X-rays. The Chandra Space Telescope is an example of one of the scopes that would have the capability to see that in that wavelength range. And yeah, actually, here's a good time to jump back to our spandex universe here. Because there was one demo that I forgot to do, and I'll do that quickly here. Grabbing some marbles.
Can I come close to it?
Yes, if anyone that can't quite see, you're welcome to come up a little closer. Just know that you may be on camera.
Well, this is the same thing, but infinitely times d.
Right. This is just a model. If we try to simulate a black hole in here, I don't think we'd be around for long. So we're not going to do that today. But what we're going to do is we're going to talk about that stellar deflection first, which is where we got. If this is the sun at the center of our view, and over there, right across from me, if you're the Earth. When we talked about that stellar deflection, we talked about how the curvature of space-time actually allows us to see stars behind our sun. And if I can get this right, it may take me a couple tries, but I'm going to try and deflect a photon of light coming from another star so that you as the Earth can see it. So let's see if we can get this trajectory right. Here we go. Here comes the photon, and it deflects, right? Now, it didn't go quite towards you. I think I need to move a little further off to the side and try and do that same path. There it goes. That's just about perfect.
It
And
fell out.
it hit the Earth.
It
So
escaped.
that's the stellar deflection in action. Now, what you just simulated there was an example of just a spacecraft coming along, and let's say it just shut off its engines. It just falls right in. So you need this trajectory, this kind of tangential orbital velocity to get a successful orbit. Now, this isn't a perfect model because there's one thing that's working against us here. Well, you could even say two things, and that's friction. So if we didn't have to worry about both air friction and the friction of the spandex itself, these objects would keep moving. That was devised all the way back to Newton's laws. An object at rest will stay in rest. An object in motion will keep going in the same direction, the same vector path, unless it's acted on by another force. In this case, we're working against the force of friction. So when we try and get something to a stable orbit, it will always fail because in our environment, we have those sources of friction. So we will certainly open this up for a full demonstration at the end of the program. So I will welcome you to return to try this out yourself. But this also demonstrates how you can successfully orbit a black hole. It's the same mechanics, but it's just a different level, a different size of gravitational source. So if we one way to really demonstrate a singularity is to actually go underneath, and you can pull down to add some gravity, add some mass, and we could try that too.
Can I show the definition of a black hole and how how heavy the mass is?
How heavy the mass
Yeah,
is?
so we can compare it on there.
I'll have you hold out just for now, okay? And we'll return back to this at the end. All right, kids, I promise I'll let you try this out for yourself. That's why we got it out for you, okay?
Thank you.
Thank you. So, I'm going to try and conclude here shortly. We're running a little low on time, but this gives you a nice outlook on just gravity from a nice stable source like Earth. And you can throw a ball up into the air, and at higher velocity, it'll take longer along that arc because it'll reach higher into the sky and then come back down. You may have heard about the cannonball analogy. If you launch a cannonball horizontally or at a tangent to Earth's surface, you could effectively put it in orbit as long as you reach a high enough speed that it can actually just skip the curvature of the Earth. And as long as it can sustain that speed, it'll keep orbiting around our planetary body. So that's with mass. But as we know, gravity can also pull light. And for a black hole, light won't escape. It is still bound to a gravitational source. And we see this with the sun, with that stellar deflection. But with a black hole, it's so high in gravity that the light ray won't escape. So it's a similar effect. With mass, it happens on any planet. With light, it'll happen around the black hole. And here's another depiction of that. Gravity bends the path of light. So for a regular star, light is going radially outward. A neutron star, the light from the neutron star itself will actually be bent because neutron stars are hyperdense. Going up to an even more massive neutron star, light coming in will start really warping around it, and then once we reach a black hole, the black hole isn't emitting light for one thing, so this is light near it, like starlight, for example. It will just be absorbed, or it can, for stars that are further out, they can actually wrap around and give this gravitational lensing effect. Galactic superclusters draw it. We'll see this with James Webb images a lot. You'll see this gravitational lensing around structures of large mass. And when we see a picture of a black hole, it will kind of show you how the light works around it and collects. So here's a spiral galaxy. In fact, this is a depiction of the Milky Way. Not a real image, because we can't get a real image of our galaxy. But we can piece together what it looks like from the inside. And you can see we have names for the spiral arms that are near us. We're in the Orion arm. You can see we're about 2/3 out from the core. This is the center of our galaxy. And you can see how the brightness of the galaxy for spirals increases as you approach the core. So this is where that supermassive black hole lives, and where you get this high density of starlight. And this is the Chandra X-ray telescope actually looking into the core of our galaxy. So you can see the stars that are nearby. And you're not seeing the black hole there, but you're seeing its influence. And it gives you that other depiction of some of those jets coming out. Oh, actually, you know what? This I'm sorry, I missed a slide behind here in my head. This is I think M87 instead, where you get that jet like this for a spiral jet of material. So that happens with supermassive black holes frequently because there is a high concentration of matter there. And if we look at M87 in Virgo, this is a look at that in X-ray. This is the galaxy here, and this is the jet of material coming out of, or originating from the black hole. Not coming from within it, but because of all that concentration of mass around it, exiting from the poles of the black hole. Now, here's a view of the center of our galaxy. Looking at the stars, this is the center point, and these are the stars around it. This one's not animating, but there is an animation of one where you can actually watch. We've watched these stars closely over time, enough that we can actually see them orbiting the black hole. So again, just proving it's just the central source of gravity, and it behaves like any other high gravity source. Here is an image from the Event Horizon Telescope. This isn't just one telescope. This is many telescopes across our planet that function as one large telescope. That the thing there is that there's going to be a lot of gaps in the data when it comes to using an array of telescopes across our entire planet. Because it's not one big mirror. You basically have a theoretical mirror that's as big as the Earth, but with massive gaps inside it, and you're collecting data, almost pinpoint data from that large mirror. And when you collect it all, you are able to see, you collect enough data to produce an image of the shadow of a black hole. So we've seen a lot of imagery of black holes tonight, but this is based on real data. It's not just a point and shoot image. It requires a lot of mathematical modeling to fill in those blanks and try to assemble this image. So you see the shadow of the black hole at the center. That's, again, the absence of light. Light can't escape. That's the event horizon. There's the name. It's the properly named telescope system. And then around it, you have this material, this light being warped. This is all the energy behind the black hole that's warping around it. And there is some inclination of the accretion disk around it as well on the edges. But that is a recent, I can't remember exactly what year that was, but it is a very recent development. Even more recent is this view. That was of M87, the previous galaxy we just looked at. So that was the first image they got because it's a good face-on galaxy. You're not looking through too much material. It's tricky to get an image of our galaxy because we have to look through a lot of stuff to try and collect that data specifically from the black hole. But this is the center of our galaxy. With Sagittarius A, that's the name of our black hole at the center. And you can see the shadow at the center, and you can see the disk around it. I can't quite explain these glowing nodes here. I do not know why those are there necessarily, but that is showing you a shadow of what we've seen so far has just been theoretical. The prior pictures, the artist's illustrations, are based on theory. This depiction here, too, is based on theory. What should a black hole look like if you're up close to one? And that, again, there's that accretion disk, that orb of material around it. If you have enough mass, you'll get those jets that show up in X-ray. And it shows you kind of the view that we're getting. It shows you how we orient it and how we see it from our perspective. Ooh, and I do like that it gives you, this is the M87 image, and it gives you a sense of how big it is. So that's the size of our solar system to the farthest extent. And then it shows you a simulated image to give you an idea of, okay, what would this look like if we mapped it out based on theory? This is based on real data. This takes that data and maps it out onto theory. And you can see how those glowing nodules there. All of that, okay, so this does explain it. Yeah, material rotating toward the Earth is Doppler boosted and brighter. So it's kind of this higher density zone based on Doppler shift. So it's coming through here and glowing brighter in these zones. And then the event horizon is the exact shadow that we see there, where light can't escape. So journeying to the center of a black hole, according to Einstein, gravity bends space-time. Once you pass the event horizon, there's no going back. So let's talk about, as far as theory is concerned, and this is based on equations, and our understanding of the physics of black holes, when you cross the event horizon, as a person, when you cross the event horizon, you'll get stretched and stretched and stretched, and eventually get ripped into individual atoms. This process is popularly known as spaghettification. You start getting pulled and pulled and pulled until your body couldn't take that pull anymore, and then you get basically bifurcated again and again. It's not the best thing to picture, I guess, but it's kind of, calling it spaghettification adds a little bit of comedic spin, and it's something I guarantee will never happen to you. So it's more fun to talk about than anything else, just the theory behind it. And this process plays out again and again to the atomic level. So eventually you're just a stream of atoms flowing in to the black hole. That's what's left. And you'll never escape. What happens beyond that point, no one really knows. But that's the result of entering or crossing the event horizon. The reason you are getting stretched is because the gravity in a black hole, once you cross the event horizon, is so strong, it's actually stronger at your feet than it is at your head. So if you're just like diving in, you'll get stretched at the bottom and you'll just watch your feet drift away from you as you get pulled in. And again, not to scare anyone, because it's not going to happen. But it's, again, fun to consider, to think about. This myth says black holes will spit you out on the other side of the universe. In fact, once you're in, there's no getting out. As far as theory is concerned, that's what happens. You're stuck in your atoms. So there's no escaping. And one other, and if you're familiar with the movie Interstellar, you may recall that they were in orbit around the black hole system, and because of that high gravity, Einstein's theory of relativity explains the relation of time and space and energy. So approaching a heavy central mass like a black hole, so if you have the rocket ship here, closer to it, and one out here, time will actually be moving slower for you relative to an observer that's further out from the black hole. That's exactly what happens in that movie. It's actually a pretty good depiction of both the actual likeness of a black hole, what it'd look like to be near it, and then the time dilation process that plays out based on your approach to the black hole itself. So time starts moving slower, and it is effectively, if we could find a heavy source of gravity like that near us, it's the most effective way to time travel. It lets you time travel into the future, not the past. And currently there's no direct way to manage that other direction. But if we had a nice convenient black hole to go to and we sent someone near it, then it would be an effective way to travel into the future. Okay, and that about wraps up our black hole discussion. For the presentation, like I said, we will have this opened up for simulating and trying it out yourself. But for the moment, I am happy to take any questions. If you could just raise your hand if you have one, we'll bring the mic to you so that the live stream can hear you as well. All right, I'll give you the mic here if you want to ask your question.
So yeah, I'm going to show you the parts of the black hole right here. So that deep part in there, that is where the actual hole is, but this outer edge, that is the event horizon.
Yeah, you consider that as the model for sure.
Yeah.
And you could take your marble and, if you want, drop it in from the event horizon, let it cross over.
And mostly, it's like,
There it goes.
because, thank you. I just like how you teach me.
Oh, well, thank you. I like how you taught us right here. Oh.
So my question was, when we're looking at the black hole, we see the, what do you call it, the disk around.
Like that, the accretion
The
disk.
accretion disk. but then there was the energy things. What is that? Is that ejecting mass? Is that ejecting energy that we're just observing in sort of in a light form? What are we observing in that moment there?
Sure. So if we can go back to that image, I'll show you that. Just down to the moment. Let's go back here. This is a good one. So this shows the accretion disk itself and the material. Now, the process that plays out here is driven by the magnetic field around a black hole. And this is, you can see how it almost forms a plasma here. So this is in part light, but it is particles of mass as well. From, like I said, in most cases, it's from stellar material being pulled in. It's from a large amount of mass, from most likely from a star nearby, being broken apart, and that mass coming into the accretion disk. And you can see it's not emitting from the edge of the event horizon itself. It's just above it, so it's driven by the magnetic field around the black hole. As this material coalesces around the disk, it feeds up into here and becomes a jet of ionized particles. That's the best way I can describe it, but there's certainly, you can certainly look up a proper simulated view of why that process plays out.
How quick does that happen?
That I don't know. Presumably, as soon as there's a mass threshold, I'm not entirely certain, but that's my best guess, is that there's a mass threshold it reaches, at which point it's able to start emitting those jets. Any other questions from the audience? Any questions from the...
Mike Blake asks, any thoughts on the recent James Webb Space Telescope and Chandra finding very early black holes about 480 million years ago Big Bang?
Okay, so yeah, that is like, we kind of dipped into that a little bit earlier, where they are discovering these the black holes, not just the evidence for individual ones, but also the ones at the center of our spiral structures in the very early universe. And he pointed out like 500 million years after the Big Bang, something like that. There is a point where we can't look past. The universe becomes opaque early on in the stages of the Big Bang, or like the course of that millions of years timeline. We can't see past that point. So we don't know exactly what's going on in there besides what physical theory tells us. But James Webb can look closer, further back in time to the origins of the Big Bang, to the point where we can see some early stages of galactic formation. And again, because of some of the earliest galaxies show signs of spiral formation and presumably a supermassive black hole at its center, clearly this started happening pretty early on, because a lot of those stars were probably fairly massive. And as soon as those stars collapse, you get a black hole. So they've been around since the early stages of the universe. And again, they have to be factored in to galactic formation, because especially now that we know it happened so early. They may be a driving factor for that, but we don't know for sure yet. Okay, any other questions? I'm not sure yet about that. All right, let's turn this mic off. And with that, that does wrap up the presentation side of things. We will, if the sky's still looking decent, we will have the telescopes open. And the rule at Kopernik is to, if you're here and the skies are clear, you got to go out and look through a telescope. So if you haven't yet, make sure you do. If you don't get to see anything through a telescope tonight because of cloudy conditions, make sure you see one of the staff on site so that we can give you a complimentary pass. But I'm hoping it still stayed clear enough that we can see the moon or the planets. And also, if anyone wants to try out the black hole simulator, I will have this available up front for you to grab some marbles and try getting things in orbit, try that stellar deflection action, just simulate a black hole. And thank you for joining me.